Hello, calculus people. Hope you're having a fantastic day today. Today we're going to be talking about our very last lesson of the year, at least as far as the AP test is concerned, growth and decay. This is actually a pretty neat little guy, little setup here for it. It says every solution to the equation dp over dt equals kp can be written in the form p equals p e to the kt. What this is saying is that if you ever come across a differential equation that is just a constant k times your value of p, that you can rewrite it as p equals p sub 0, which is your initial value, times e to the power of kt, where k is less than 0 representing decay. So if k is less than 0, that means the population is going to be decaying, or the temperature of a cup of coffee is going to be decaying, or something along those lines. If k is bigger than 0, it represents growth. So a population growing. Now this actually makes your job really, really easy if it fits to this format first. And I'll show you an example of that in example number 2. For example number 1, it says a cup of coffee at temperature 180 degrees Fahrenheit is placed on a table in a room at 68 degrees Fahrenheit. Now this is the typical calculus question. You put a hot cup of coffee on a table in a room that's colder than the coffee. The differential equation for its temperature at time t is dy dt equals negative 0.11 y minus 68 and y sub 0 equals 180. This is my initial condition. Now, if you would notice, this equation does not fit this format of just Kp, so I can't use my step here, so I'm just going to move this up for a second. So question A says, after 10 minutes, what is the temperature of the coffee? And I can almost guarantee there will be a question like this on the AP exam. Most of them I've seen have involved coffee. Not sure why. Teachers love coffee. Why not? So A says, after 10 minutes, what is the temperature? Well, what they've given me is the differential equation for its temperature. This is the rate at which the temperature is changing. And they want temperature. So I'm going to have to solve this differential equation, right? So let's see what we can do. What is the temperature? So I've got dy dt. Start out with the original equation here. Negative 0.11 y minus 68. And I am going to see if I can find out what y is. All right. So let's see what kind of trouble we can get into here. Where am I at here? Getting these alone, I need my y's on this side, so this is going to be 1 over y minus 68 dy. So I'm just dividing by y minus 68, negative 0.11 dt. All right? And then we can integrate that. And this is going to be the natural log of y minus 68. See, I don't need a u substitution here because it's just 1 over u. And the derivative of that is just 1, so there it is. So I don't really need a u substitution here. And the integral of this, we have negative 0.11 t plus c. So I'm going to calculus magic both sides. We e both sides. We get y minus 68 is going to be e to the negative 0.11 t plus c. Y minus 68 equals, and just for the sake of time, we learned this yesterday, that this plus c is just going to drop and become ce to the negative 0.11 t. Remember, that's in yesterday's lesson. If you'd forgotten how to do that, you want to go back and check it. And use your initial condition. So my initial condition is 180 for y. Sorry, it's up here. 180 for y, 0 for t. So 180 minus 68 equals CE to the negative 0.11 times 0. So e to the negative, or it's e to the 0 basically, is all 1. So 180 minus 68 is 112. C equals 112. Plug it back into the one you got it from. So y minus 68 equals 112 e to the negative 0.11 t. And then just add your 68 over. Y equals 112 e to the negative 0.11 t plus 68. Now to answer the question was asking, after 10 minutes, what is the temperature of the coffee? All I have to do is plug 10 in right here. So I took the rate at which the coffee was changing and integrated it to find its actual temperature. That's all this to here. So I've integrated it, I've solved for y, I found the temperature. Now all I have to do is put 10 in for time. And I've already done this ahead of time, so I'd like you to write this down here. The temp is 105.281 degrees Fahrenheit after 10 minutes. And that's just from doing it earlier. I plugged a 10 in for T right here, and you get 105.281. This is a good opportunity to check that. Is that cooler than 180? Well, yeah, and that's to be expected, right? If you got 185, obviously the cup's not getting hotter, is it? Also, if you get a freezing number, like if you got a number lower than 68, then you also know something went really wrong, because the cup's not going to get any colder than the room is. All right, part B. Part B says approximately how long does the temperature of the coffee, how long does it take for the temperature to drop to 75? So what I'm doing is setting my y value down here to 75. So how long does it take? I'm going to say 75 is equal to 112 e to the negative 0.11 t plus 68, and I'm going to solve for t. So subtract your 68 over, and you get 7 is equal to 112 e to the negative 0.11 t. Divide both sides by 112, you get 7 over 112 e to the negative 0.11 t. Natural log both sides. You get the natural log of 7 over 112 is equal to 0.11 t. Right? And so all you have to do here is divide by 0.11. And when you do that, you get approximately 25 minutes. And I can show you that here in just a moment. Natural log of 7 divided by 112 divided by 0.11, and it's about 25 minutes. Now the fact that, oh, I'm sorry, I forgot the negative. I was wondering why it was negative, so I forgot the negative here. So it would take the negative out, right? Just make it positive 25. So it's about 25 minutes. And of course we would round that, so 25.20, I messed up. 25.205 minutes. And then C, sorry to just blaze along here, but I want to make sure to get to the back one here. Find the average temperature of the hot coffee during the first 10 minutes. Keywords, average temperature. You know the temperature came from the integral, right? Well, the average temperature is going to come from the integral of that. This is basically saying find the area under the curve, but it's an average area. So I want you to come down here just so you'll remember here, average temp, it's 1 over b minus a, 1 over 10 minutes, so it'll be 10 minus 0 because you started at 0 minutes. And it's the integral of 0 to 10. Remember, this is your averaging out here. 112 e to the negative 0.11t plus 68 dt. So you're averaging out your integral. You're averaging out your area. And you find that the average temperature is 135.926 degrees Fahrenheit. And that's just all calculator work. All right. So from here, I do want to give us a chance to use the shortcut. So the second question does deal with that. And I'm excited to show you this because it's pretty cool. Example number 2 says at any time t is greater than 0 and days, t is measuring days here, the rate of growth of bacteria population is given by y prime equals ky. Okay, y prime equals ky. As soon as I see that, bam, dt, or dp over dt, this is the derivative of p equals kp, the derivative of y equals ky. I can use my shortcut. This is awesome. K is a constant and y is the number of bacteria present. The initial population is 1,000. There's your initial condition. So the initial condition is 1,000. And it says the population triples during the first 5 days. Now you have to think kind of outside the box for this one. Population triples in the first 5 days. That means when time is 5, that your population has tripled, 3,000. And you're going to see several references in here to population tripling or multiplying by a factor of 6, multiplying by factors of this, factors of that. And it's all good and stuff. We'll make sure and point that out when you get there. So part A says write an expression for y at time t equals 0. So I'm starting out with y prime equals ky, or in other words, dy dt, I am with respect to t here, equals ky. And what's cool about this is that I can jump straight down to y equals y sub 0 e to the kt. And I got that from over here. So when you're in this format, I have dy dt equals ky, so just replace p with y. You get y equals y sub 0 e to the kt. Now, I know you're not just going to accept that because you're a calculus student. You need proof. So here's proof. dy over dt equals ky. So get your y over here, it's 1 over y, get your dt over here. 1 over y dy, k dt. Integrate both sides. You get the natural log of y, kt plus c. I wrote this on a paper so I don't have to put it on the notes. E both sides, you get e to the kt plus c. And you know that using calculus magic here, you can pull e to the c down, you get c e to the kt. C here just has a very special value. It happens to be the initial, y sub 0. And the initial here, y equals, the initial 1,000 e to the kt. Back in Algebra 1 and Algebra 2, we call these exponential growth and decay formulas, and you mainly used it for money. But it can be used for anything that grows. Excuse me. Anything that grows exponentially, that is. All right. So from here, we have y equals 1,000 e to the kt, and that's from using a shortcut, which is fantastic. I love shortcuts. I'm all about shortcuts. So from here, what we have to do is use our initial condition that it gives us, And it would be great if we could use 0, but we can't. We've already used it. So I'm going to use the point they gave us, 5, 3000. And I'm going to figure out what t is, or excuse me, what k is. So I have to solve for k. K is kind of like your unknown constant value. So we've got to solve for k. So let's do that. When y was 3000, 1000 e to the k times 5, and that came from my point. And I'm calling that an initial condition. Even though it's not the condition that at the start, it's still a point that they give me that I can use to figure out my k value. So divide by 1000, you get 3 is e to the 5k. Natural log both sides. You get the natural log of 3 equals 5k. So k is the natural log of 3 over 5. The natural log of 3 over 5. So my value then, y equals, go back to here, 1000 e, my value of k is the natural log of 3 over 5 times t. And t can go anywhere in here really, it doesn't matter. And using the property of exponents, the properties of exponentials, properties of logs, you can actually simplify this down even more. But we'll get to that in a minute. So, where are we at? Have I answered the question? What does the question say? Write an expression for y at any time t equals 0. And you know what? I am going to simplify this just a little bit. I don't like the way this looks. E to the 5 over 5, this is t over 5. E to the natural log of 3 is just 3. Let me simplify this a little bit. Y equals 1000. E to the natural log of 3 is just 3. So let me kind of split this. I'm going to show you where I'm going to get this from because I don't want to just do this blindly for you. This is like saying times a fifth times t, right? Well, e to the natural log of 3 is just 3 because e and natural log cancel out. So I can do this and call it 3 to the t over 5, and mathematically I'm okay. I'm sound with that. And that simplifies it a lot more. I don't have to worry about this e and this natural log anymore. And yes, this is perfectly okay. E to the natural log of 3 is just 3. So it's 3 to the t over 5. And that's going to make part B a lot easier. Okay, part B, these were from pre-cal, by the way. If that looks a little fuzzy, that's why. I'll give you some help tomorrow if you need it. Part B, by what factor will the population have increased in the first 10 days? So basically, what I want to figure out is what is y of 10. Plug in a 10 for t. Here's 1000, 3 to the 10 over 5. Well, 10 over 5 is 2, 3 squared is 9, so y of 10 is 9,000. And they're mowing today, which is fantastic, apparently. There's not a more perfect time to mow than when I'm trying to record a video. So anyway, the population was 1,000, now it's 9,000, therefore pop increases by a factor, excuse the spelling there, by a factor of 9. It was 1,000, now it's 9,000. Bam! Bob's your uncle, factor of 9. Let's go back up here, part C, almost there. At what time in days will the population have increased by a factor of 6? Well, if you start with 1,000 and you increase by a factor of 6, that makes you 6,000. Yay! Population formula is still 1,003 to the t over 5. So divide by 1,000, you get 6 equals 3 t over 5. And we'll have to get rid of this joy of joys. We'll have to natural log both sides. So the natural log of 6 is equal to, and we have to use a law of our exponents, our property of logarithms, rather. Here they come again. It's like the flight of the Valkyrie. Take your exponent down. T over 5. The natural log of 3. Somebody just shut my door. They got tired of me singing. Real quick, let's try and finish before he gets back. Divided by the natural log of 3 and times 5. 5 ln 6 over ln 3 equals t. That is approximately 8.155 days. So the population will increase by a factor of 6 in about 8.155 days. All right, last one, D. D says to use a trapezoid rule. Ooh, trapezoids. With 3 equal subdivisions to estimate the total bacteria after 6 days. Okay, this should be fun. So I've got from 0 to 6 days using 3 subdivisions, 3 parts to it, rather. So remember, it's b minus a over n, which is 6 minus 0 over 3 subdivisions. So every one is 2. So this is 2, this is 4. All right, so if you'll remember, it's 1/2 times this value times 1,000. Remember that it's the function to the original, so 1,003 to the 0 over 5 plus, and it's 2 times all of the insides. So it's this same thing with a 2 here, 4 here, and then the last one will be outside of that. So it's 1,000 times 3 to the 2/5 plus 1,000 times 3 to the 4/5 plus, am I going to get it in? Will it fit? 1,000 E. Where's E coming from? It's not going to fit. 3. So close. To the 6 over 5. Continuing on the desk. That's okay. And there it is. And I've already punched that in the calculator here. When you punch it in, you get 12,657 657.333 bacteria. So just a trapezoid rule for you. Remember, this is the function at your left value, doubling the ones in the middle, and then your function at your right value. Woo!